Okay, so week 3, part 3, we're ready to start looking at some. This is what caused Huygens to believe that it was waves that they were looking at. This kind of behavior, what we're seeing now, which is we have these horizontal waves marching towards this opening. Now, remember, these horizontal waves are made up of these droplets coming all in a line. So in a line, they're all approaching this blocking obstacle, right? But the top guy doesn't get to go through, because that guy is blocked. This wave front will continue to go through. And notice that there's nobody back here. This guy was giving some interference to him, which was dampening out all of that stuff that was going in kind of a curvy direction. So now when this guy gets out here and he's able to spread his wings and fly, it's going to give a curved thing to the edge. Now, he's still going to have more waves below him, so that explains this part where we're still parallel. And then down here, this wave lost its interference, and so that's why we get parallel lines in the middle, and we get these curved waves coming off at the edges. That's diffraction. So really, this should be diffraction. It appears like the wave is changing, right? But really what we're doing is we're turning off the noise dampening headphones on the top part of this wave so that those waves, which were there before, we're just not dampening them out, are now free to go out there. Now, as this opening gets smaller and smaller, we'll let this guy be the one that gets to expand this time. When it gets close to a measurement of the actual wavelength, that's when we get something which is closer to the real spherical wave front going through, right? So here we're basically stripping out all of the parts which weren't part of the original. We dropped a single drop into water. So you're stripping out all the stuff above and below. The closer you get down to here, then afterwards it will look like you have let just one drop fall, right? Because only one wave got through, and it is radiating out in all directions, and that's why it starts to look very rounded as we come down close, and it comes back to pure radiation in all directions. That was what I was trying to show very poorly in week 8 with this kind of craziness diagram. This is like all these little dots coming off at the edge, because that's what even a circular wavefront is made of. And I think this was more about letting light out of a flashlight, where you have a kind of, here they're all trapped in their parallel waveness, and then as they get down and the waves grow, they can start to grow outside of the bounds of their interference. All right, and we talked about how this is like noise cancellation. The interference, basically it's the opposite of noise cancellation. We had a situation where one wave on top of the other was canceling each other out. We took this wave away, and what we got was the original wave free to go out through all of its waves. Now this seems really sophisticated, and it's kind of, well, how would Huygens have figured this out? But they could observe this in nature, because this is wave behavior that we can see happening in the oceans. We see it in all forms of waves that we can look at. So diffraction, bending at openings, diffraction happens with sound. Diffraction happens in all sorts of things. We're going to do, there's an amazing thing by, I think it's the Exploratorium, where we're going to build a Fourier filtering device to filter out different waveforms. I'm very excited about later on. But this wave behavior happens with all physical waves that we can see. Now sometimes the behavior is dampened by gravity, just like when you turn dampening on with your resonance exercise. So sometimes we don't perfectly see what light does, or what a continuous wave does, because the effects due to gravity are just overwhelming, seeing what the natural propagation of the wave would be. Diffraction also occurs not just at whole openings, but as you go around any obstacle, because basically there is a wave here that was dampening out the round waveness of these two waves that gets blocked, and they're free to expand on their way on the other side. And here's an example of that happening in ocean currents, or in ocean waves. These are surface waves. So we have waves coming in, a whole bunch of waves, and they're definitely interfering with each other. They go through an opening. I love this. They go through an opening, and now look at how it's much more clear a set of what waves were allowed through that opening and what waves got stripped out by this opening. But it's not just diffraction into an opening that we see, but around the other side here, notice how we have these round circular wave patterns coming off here. These are also set free of all the waves that were blocked by this obstacle. So diffraction happens around obstacles, and it happens when you go through an opening. Okay. Refraction is when we change the path of a wave based on changing speed, when you go from one medium to another. So this is light going from air, which is pretty close to the speed of light, through glass, which is 40% less than the speed of light, for how quickly a pulse will make it through. And not really like a pulse wave, we would call this a group. A group of light waves would make it through 40% slower. The group speed through this media would be 40% slower. So yes, when you look at before and after, this group of light, photons, waves, whatever, the group will depart 40% slower than if this was going through, than if this space was air, if you measured where the group was and where the group exited. We'll talk about the Muggle and the quantum in a little bit. Refraction also occurs in other media. I'm going to pause for a bit, and I'm going to actually get you the GIF of this jello. It's just something I got from the web, but I just want to show you that, so I'm going to pause for a sec. Okay, so here's our funny jiggling jello wave. And it's fun because it's so different than if we watch this wave go through water. A wave through water would be going much quicker, and the wave through jello is silly and fun, and it jiggles like a bowl full of jelly, just like the Christmas Carol, or the Christmas, 'Twas the Night Before Christmas. This also happens in air, where we see waves bending or changing the direction that they're going in based on different speed through a medium. And what we have here is a difference in speed changes the viscosity of air, and we have a difference in the speed of this air and a difference in the speed of this air behind this island, which is an obstacle. So there's a difference in speed between these two airs, which means one has more molecules you can think of, it's thicker, and the other one has fewer molecules. Bernoulli effect is part of what explains this. And we can see that these regular waves that we would expect start bending at an angle. So this is refraction of a wave. On our website, on our Haiku, please watch Mr. Anderson, that's how he refers to himself, and he has a whole series. Bozeman Science is a great series, and in the video that I have for you, the first half will take you through the marching band, why this happens, and this is a very important concept to get, of the marching band of why the wave refraction happens, and why it changes the angle. And to get that analogy is very important. We're going to see that that analogy doesn't cover everything. But we're going to do that and talk about Muggles in our next video. All right, see you in the next one.